All right, let's talk about chemistry. It has its own special language, a way for scientists to write down exactly what's happening in a reaction. Today, we're going to crack that code. We're going to learn how to write the amazing stories of transformation that happen all around us. So think about it this way. How would you write a recipe for a chemical reaction? It's kind of the same challenge, right? You've got your ingredients, you mix them together, and you get something totally new. Chemists needed a universal way to write that recipe down, and that's exactly what a chemical equation is. We're going to start with the absolute basics. Step 1, the word equation. This is pretty much exactly what it sounds like. It's the most straightforward way to write our chemical recipe, just using plain language. So, what is a chemical equation officially? Well, you can just think of it as a form of scientific shorthand. It's a super clear, concise way to show what goes into a reaction and what comes out of it. It makes sure every scientist everywhere is on the same page. Let's break down the basic grammar of our chemical recipe. See those substances on the left? Those are the reactants. You can think of them as our ingredients. And on the right, those are the products, our final dish. That little arrow in the middle just means yields or produces, and the plus sign means reacts with. See, it's a pretty simple system when you look at it like that. Okay, here is a classic example. Hydrogen plus oxygen yields water. That's it. That's our word equation. It tells us our ingredients, and it tells us our final product. We're going to keep coming back to this simple little recipe as we get deeper into the language of chemistry. Now, word equations are a great start, for sure, but they're not very detailed. To get more precise, we need to level up our recipe to what chemists actually use. It's called the skeleton equation. Let's see how this takes our recipe to the next level. And here is that level up in action. On the left, our simple word equation. On the right, the skeleton equation. See what we did? We just replaced the words with their chemical formulas, H2, O2, and H2O. Now, this is more than just swapping out symbols. This is a huge leap in how much we know about what's going on. Because a skeleton equation gives us so much more information. It doesn't just say water, it says H2O, which tells us that every single molecule of water has 2 hydrogen atoms and 1 oxygen atom. That kind of detail is absolutely essential if you want to do real chemistry. Okay, before we go any further, we have to pause. There's a really crucial rule we need to cover. Getting this right is the key to writing our chemical recipes accurately. I'm not kidding. You have to know this rule. See, some elements out there are, well, they're kind of social. When they're not bonded with other types of elements, they don't like to be alone, so they pair up with themselves. And you always have to remember this. This whole idea is called a diatomic element. Let's break that down. Di means 2, right? So these are simply elements that exist as 2-atom molecules. This is why the hydrogen in our recipe isn't just H, it's H2. The oxygen we all breathe isn't just O, it's O2. They're always hanging out in pairs. And here they are, the Super 7 diatomic elements. You're definitely going to want to remember these guys. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So from now on, whenever you see one of these elements standing all by itself in an equation, you gotta remember to write it with that little subscript 2. Okay, practice time. Let's try an example. Imagine you're told sodium reacts with water to produce sodium hydroxide and hydrogen gas. How would you translate that into a skeleton equation? So, what do you think? What's the skeleton equation gonna be? Take a close look at the products. We've got sodium hydroxide and hydrogen gas. Remember that Super 7 list? One of those is right there, all by itself. So what should its formula be? And there it is. Now for sodium, H2O for water, NaOH for sodium hydroxide, and look at that, H2 for hydrogen gas. See, we write H2 because hydrogen is one of our Super 7 diatomic elements. This is exactly why that rule is so important to remember. All right, we are so close. We've leveled up from words to formulas, and we learned the super important diatomic rule. Our recipe is almost perfect. There's just one last final step to make sure it's 100% scientifically correct. Let's go back to our water recipe for a minute. H2 plus O2 equals H2O. I want you to look really closely at this. Let's count the atoms. On the left side, we start with 2 hydrogen atoms and 2 oxygen atoms, right? But on the right side, in our final product, we still have 2 hydrogens, but only 1 oxygen atom. So where did the other oxygen atom go? Did it just disappear?
No, of course not. And this brings us to a fundamental, unbreakable law of the universe, the law of conservation of mass. Basically, it means matter cannot be created or destroyed. You can't just lose an atom in a chemical reaction. You have to be able to account for everything you started with. Our recipe has a missing oxygen, which means it's not quite right yet.
So how do we fix this? We have to balance the equation. We do this by adding these big numbers out in front of the formulas. They're called coefficients. So by putting a 2 in front of the H2 and a 2 in front of the H2O, we're not changing the chemicals, we're just changing the amounts in our recipe. Now let's count again. On the left, 4 hydrogens, 2 oxygens. And on the right, 4 hydrogens and 2 oxygens. Perfect. The equation is now balanced. And there you have it. That's our 3-step guide to writing the perfect chemical recipe. You start with a simple idea, the word equation. Then you translate it into the language of chemistry with a skeleton equation. And finally, you make sure it follows the rules by balancing it, from a simple description to a scientifically perfect statement. When you get right down to it, that's what this is all about. Learning the language of chemistry isn't just memorizing rules and numbers. It's about learning how to read and how to write the incredible stories of transformation that are happening all around us, and even inside of us, every single second. So now that you know the language, what chemical stories will you write?